Dear students, a very warm welcome to Powertrain Controls using Matlab and Simulink. What can you expect out of this course and where will it be exactly necessary or how will it be exactly useful inside the industry? These two questions should be lingering in your mind. So the first thing is when you take the automobile industry, a lot of electronics has come in compared to the previous years, and especially with BS4 and now the BS6 norms, control electronics play a key role in controlling the emissions or the ABS, everything. So with powertrain controls, Simulink is one of the main platforms that is being used to do the powertrain controls. The main control logic is built using Simulink, and there are a lot of coders like Target Link, etc., which are being used to convert this Simulink models into codes which will be directly used in the ECM. What actually happens in the industry is there are a lot of small tasks and jobs related to this. So there is a team that writes the requirements, like how does my sensor behave or how should my actuator behave based on my real world feedback. What is the requirement? For example, if I take an EGR valve, what is the requirement for the EGR valve? How should it behave? So an EGR valve is used for controlling emissions. And how does it actually do that? A lot of sensors give information to ECU, and ECU takes a decision when to open the valve so that the emission is controlled. If I'm going to open the EGR valve always, no use. If it is never going to open, again, no use. So this decision of when the valve to be open and closed will come inside the requirements of an EGR valve. So an algorithm has to be developed, and most of the time we use Simulink to develop this algorithm. So when you take the life cycle, the first step is going to be defining the requirements of the single component, and then taking the requirements, building the algorithm. Once the algorithm is built, there is going to be various levels of testing the algorithm, and once it is tried and tested, it is going to be added to the major part of the ECM code, and it will be ready for production. So here, building models in Simulinks based on requirements is a key area, and the purpose of this course is to give an introduction to what is powertrain and why are controls necessary in this domain of powertrain. So that will be the first part of the course where the powertrain as such is going to be introduced and the importance of controls in the domain will be stressed. The second part is going to be Matlab and Simulink. So here we have tried to introduce to you some basic and key components of Simulink library, like switches, counters, etc. So what will you be actually doing once you enter the industry is the first step is we are not going to develop an entire model to control an engine or something. The first thing will be we will be getting requirements, small requirements, and for example, we might be needing to develop a small counter or a small timer. So these are the requirements, and to do this, to develop the controllers, to take decisions, to build counters, timers, etc., and take decisions. We will be using a lot of very small but powerful blocks inside Simulink, like switches, unit delays, mux, demux, bus, etc. So here we have covered all those basic block sets in Simulink and how we can practically use them to build models. We've also built a example control model using all the blocks which were taught in this course, so that you guys get a good idea on how the things happen. And as a job seeker, when you step into this industry, what is expected out of you is a basic bare minimum knowledge on powertrain and components. So this is the thing here. If you are a mechanical engineer, there are good chances that you had an automobile elective and you are already aware of the powertrain and the components. But most of the time, Matlab and Simulink is not there as a subject for a mechanical engineering student. There is less knowledge about controls. If you're from the other background, for example, EC or EEE, you might have a very good knowledge in control systems, Matlab and Simulink, but using or understanding about powertrains will be very minimal. But when an OEM seeks or a tier 1 company seeks someone powertrain controls, it is very ideal that the candidate has both knowledge in powertrain and controls, so that it is very easy for him to sync with the existing team and start building models very quickly rather than training a person on for a long time. So whenever you're going to get into the positions, most likely you will be facing questions or tests with basic knowledge on powertrain and basic knowledge on Simulink. So this course is being built in such a way that you get a basic idea of powertrain and you also get basic idea of Matlab, Simulink and the control systems. So once you done with this course and build a model by yourself in Matlab and Simulink and try it out, you should be ready or you will be ready with basic knowledge in powertrain, with basic knowledge in controls and a good knowledge in Matlab and Simulink, so that it is easy for you to get into the industry. So with this, let's get into the course. Thank you.
Now that we've taken a look at a few different engine components, different parts of the engine, different terms related to engines, and understood what these terms mean, we have to now understand the control. So before that, let's first take a look at the ECU, the one that is going to be doing the controlling. We have to first understand what the ECU is going to do, and then we'll see how we can use the ECU to achieve our control. So the ECU is just going to take the output of the sensor, and it's going to read what the sensor is trying to tell the ECU, and then based on this output, it's going to make sure that the actuator knows what to do. This is what I've been saying from the very first lecture itself. I just mentioned that the control system comprises of sensors, actuators and software. So the software is going to be the ECU in this case, and the ECU is going to be told what to do in which condition. So it's going to be given a few conditions and said that if this is the case, do this. A very basic example would again just be the temperature control system that we had taken up previously. So when we want to control the temperature, we're going to have to give a few inputs, and so we're going to have a few sensors like the coolant temperature sensor. We're going to read the oil temperature sensor, and then the air temperature, ambient temperature, and so on. And so based on all these temperatures, we're going to then achieve. We're then going to understand what we have to do. So something called as a correlation, and the value of these temperatures is called as a set point. So we want a correlation between all these set points, and then we want to see if whatever value it is giving us is not garbage. We want to understand if the value that it is giving us makes sense. So this is called as a rationality check, and we want to see if all the three values, however many values that we get, if they all make sense, if they have to be related, and then we want to understand what decision has to be made. So all this decision is taken by the ECU. So all the three sensors are going to give us pretty much the same value. So let's say one of the sensors throws out a value of 90 and the other two sensors throw out a value of 120, and this is going to tell the ECU that something is wrong. So it's going to tell the sensor that something is wrong. Two values match, but the third value doesn't match with the other two values, or it's not in a plus or minus 5 range. So this is going to tell the sensor that something looks wrong. So the ECU is not going to know exactly where it's wrong. It could just be a sensor fault, or it could be that something has terribly gone wrong. So the ECU has to take a decision. It has to make a decision that okay, I might do something. I'll just keep the vehicle safe such that it can return back. You can take it back to wherever you want to go. This is how the ECU functions. This is all the ECU does. So the ECU is essentially the CPU of the vehicle. It's going to control all the software. It's going to tell each and every system what to do. So let's take a look at how the ECU does this. The ECU, I'm going to take a look at the different parts of the ECU. So we're just going to understand what it does from a software perspective. So firstly, we have this term called as signal conditioning. So the ECU only receives signals. It receives digital signals from the sensor. So the sensor output is going to be in analog form, and we want to convert it to a readable format for the ECU. So this conversion of the sensor output to a readable format is called a signal conditioning. So we can do this by using a digital to analog converter, and this is going to convert the units to whatever, so to a digital signal, and this digital signal can then be sent to the ECU, and based on this value the ECU is going to know what to do. So this is something we would have already told this ECU that based on that if this is a set point, do this. So after it has read the signal, it then has to take the decision on what to do. So this is going to be done by the CPU or the ECU itself. It's going to have a microcontroller, and this microcontroller is going to be making all the decisions that is necessary. So based on whatever the input that is coming in, so based on the signal, it's then going to be taking a decision. So the signal is generally going to be in terms of voltage. So if the voltage is relating to some other voltage here, so we're probably going to have a plot that tells us relationship between a certain value and its voltage, and based on this plot it's going to then understand what to do. So it's going to understand that the value is here, so so this must be done. So if the value is quite high, it's going to let the system know that the fan is supposed to be running. So again, let's go back to the temperature control system. So what's going to happen here is that we're going to have a fan, and based on the coolant temperature, we're going to understand if this fan has to run or not. So if the temperature is very high, the temperature is above a certain value, the threshold value we're going to assume here is maybe 90 degrees. And if it is above the certain value, we want the fan to be running. So this is just going to be a comparative check. So we're going to just see if the input is greater than or less than 90. So if it's greater than, the fan is going to run, and if it's less than, the fan is going to be switched off. So we're probably going to have a hysteresis here, just an upper and lower bounds. So we're going to tell the system if the temperature goes above this upper bound, switch the fan, and the temperature goes below this lower bound, switch off the fan. This is just to keep the fan in a certain place such that the fan, you don't have to keep on switching it off and on. This is going to cause problems later on. So after the signal has been evaluated, a decision has been made, we then want to send this signal to the actuator. We then want to tell the actuator what it has to do. We can do this in two different ways. So this is called as a low side driver and the high side driver. Essentially what we're going to be doing here is that we're just going to be telling the signal, or rather just going to be controlling the signal, the actuator by means of a switch. We're either going to give the actuator power, or we're going to take off the power from the actuator. So this is going to ensure that the actuator either runs or it doesn't run. So this is going to be done by two different methods. I'll get to the third method later. So the two different methods are low side and high side drivers. So for a low side driver, we're going to have a switch that is going to be connected to the power supply and the actuator, and then the high side driver is going to be connecting the actuator to the component. So we can either cut off the power supply to the actuator, or you can cut off the power supply from the actuator. Essentially, we're only going to do one thing. We're just going to make sure that the actuator either runs or it doesn't run. It's cut off from the component, wherever the signal is going to go to finally. And then there's something called as a bridge driver. And a bridge driver is going to either give you a positive or a negative. So either you're going to have a forward movement or reverse movement. This is required more in the case of motors, where you want forward motion, and if you're under braking, you want backwards motion. So something called as regenerative braking. And then so all the systems have a self-protection function. So as I mentioned in the previous slide and the previous example, I said that if the correlation or if the rationality doesn't check out, we want to make sure that we have some safety measure in check, such that the systems don't get destroyed. So this is where we want something called as a fault. So if there is a fault, if there is a problem, we want to make sure that the vehicle at least goes to where we want it to go. We want it to at least move on till a repair shop or something. So and then we come to the CAN bus, the controller area network. So this is a connection between all the different sensors, actuators, and the ECU. So in a vehicle, we're going to have many number of control modules. We're going to have the powertrain control module, the engine control module, and so on. So we want all the signals to be read, and we want all these. So we want all these signals to then see which signal takes precedence over, or which signal needs to be read first, which signal needs to be used to make a decision first. We want to see which takes more priority. So based on this, so this is all going to be the control area network job. Many devices are controlled to the same local area, to the same network. We can use it to transfer data. So this is going to be essentially what a controller area network is going to be. So this is going to be where all the devices are connected, and from here all the decisions are going to be made. So this is again for the purpose of safety. So this is international standard that was accepted in ISO 11898, so that we can increase the safety of the vehicle running conditions. What's going to happen here is that all the sensors are then going to give the input, and the CAN bus is then going to make the decision on what it has to do or not. So very simple example would be the automatic start or stop in vehicles. So all these different inputs going to the ECU, and then here the CAN bus will then make the decision if all the systems are in. So the car is in idling, the steering is not moving, then maybe the air conditioning, and the engine temperature, and so on. It will make a decision. Okay, so the vehicle looks like it's stopped, and the position of the brake and all that. It's going to, okay, the vehicle looks like it's stopped. So let's just cut off the engine for now. So this is all going to be made by the CAN bus. So, and then we're going to move on towards the software standards. So we can see here that we have software model and real world model. And you can see here there are different things called as abstraction layers. So an abstraction layer is an algorithm. So it's something that is readable across all different softwares. The ECU has to be written in C++. So we can't have different softwares, but different companies use different softwares. So this is something, or it's going to be a Simulink model. So we want everything to be converted into a C or C++ format. So the best thing we can do here is write or use algorithms. So an algorithm is called as an abstraction. So we're going to use all these different algorithms, and this is so that different people can use different approaches and get to the same thing, get the same functionality. So for all these different common functions of vehicles, instead of everybody doing writing a different, or if everybody comes up with a different method to do it, so we have a lot of accepted standards. All these standards are going to be governed by these abstraction layers. So we can see that here, this is the AutoSAR software architecture. So the AutoSAR was accepted worldwide as a standard by a few major companies. So this is so that the AutoSAR architecture can be used as a vehicle standard. So we don't want different people doing different things. As I mentioned in the previous slide, we have a standard such that it's going to save a lot of time and money. We don't want everybody doing different things for the same purpose. So this is how an AutoSAR structure is going to look like. It has a lot of different components. It's going to have a microcontroller, and then a few microcontroller abstraction layer, ECU abstraction layer, and then services layer, and it's going to have a runtime environment and an application layer. So we'll start first off with the microcontroller abstraction layer. So microcontroller abstraction layer is going to be different components like the analog digital converter, or the microcontroller unit itself, and then so it's going to be directly connected to the microcontroller. So you can see here we have the microcontroller abstraction layer, and directly below the microcontroller abstraction layer we have the microcontroller. And then we have the ECU abstraction layer. So this ECU abstraction layer, it's going to be independent of the microcontroller. Just going to read the microcontroller abstraction layer. So it's going to just take the ECU abstraction layer is just an interface that can access all the functionalities of the ECU regardless of the microcontroller set point. Then the services layer is going to be the operating system or the communication system inside the vehicle. So it's going to determine all the memory requirements, so whatever software, all the diagnostics, and so on. And then the runtime environment is going to be the interface between the application layer and the software. So the basic software we can see here is the services layer, ECU abstraction, microcontroller abstraction layer, and the drivers. So it's going to, the runtime environment is going to be the interface between the services layer and the application layer. In the application layer, or the software of the ECU, is just going to be an interconnected system. So these are all the different members of the AutoSAR structure. You can see here that core partners are Volkswagen, Toyota, Daimler, GM, BMW, Ford, and so on. So all these guys, they came together and decided that we needed a vehicle standard, we needed an ECU standard. For the same functionality, everybody can just use the same algorithm, and then if they wanted something else, they could then go ahead and do whatever they wanted with it. And finally, so this is just one software model. It's called as the VCycle. You can see here it's called as a VCycle because the process is, it goes from writing down all the different requirements to the coding stage, and then from the coding stage it goes up all the way doing checks. So all these checks are to see if whatever our requirement is, if it is satisfied. So we can so all these systems related. If we draw, so we can see here. So software requirements, and then software validation and software validation. So the validation is going to be running the software and seeing if it works or not. And then requirements, and then software design, software verification plan. It's going to go to the software integration. Software integration is, so the software is going to be input to the vehicle, and they're going to be seeing if the rather it's just going to be the ECU. It's going to be seeing if the ECU gives the makes the appropriate decisions based on whatever we want it to do. We will be taking a further look at the software VCycle in one of the next lectures. So for now, this is just a basic introduction to the different systems that is being used for the ECU.
Dear students, hope you've gone through this course and hope this course has been helpful to you and imparted knowledge which was not there to you previously. So we've gone through various components in the powertrain. We've understood about powertrain. We've also gone through various Simulink library box, and we've also built a sample control system so that we understood what was a calibratable, what are the basic necessary things, or what are the factors, key factors which we have to have in mind in building a controls model. I hope this will serve as a base when you're going to attend interviews or when you get a job. I hope all these things will come in handy. And so, how do you keep yourself prepared? So, on the powertrain front, there is something always happening on day by day basis. Some OEM is launching a new powertrain or a new vehicle. So, please be updated on that because the technology keeps changing. For example, now previously turbo diesels were the norm. So after BS6, we see turbo petrols have become the norm. Tata has already launched a turbo petrol, which was in Nexon, which is expected to come into Altroz. The Mahindra has come up with the M Stallion set of turbo petrol engines. So there's a technology shift. So every time an powertrain is announced, please take a look into an engine. You will learn something new. And with Matlab and Simulink, try building your own models, experiment, learn. So always one thing which I believe is when you do experiment, when you fail, you learn a lot of things so that you repeat the experiment and you succeed. So this is very necessary. So this course can just be a starting point. So this course is like just to bringing you into this world of powertrain controls that is existing within the industry. So I hope this course was a good starting point for you guys, but this is just a starting point. You guys need to update yourselves on what is happening. If an automatic transmission is launched, what is an automatic transmission? How does it differ from a CVT? Those things you guys need to update yourself with the current industrial technology. That will be of a major help. And with Matlab and Simulink, try experimenting new things. So, and if you have readily available kits, and if you have some student license, and if you are able to generate codes, and if you are in universities, you have always the student license. You can always, buy sensors. You can getting a board is not that hard these days. You can try flash, experiment, and learn things. All right. So enjoy your learning. Have a great career ahead. Thank you.